Hi, this is Kevin. Welcome to part two of my lecture for chapter 7 of the Zelle third edition Python book. And in this chapter, we're deviating reasonably from the slides that came with the book and from the book in order to include examples that are not so math heavy and some that are a little more practical. So the last thing we did in part one is we did a program called Decisions 15 Multi-Way Extended. And this is the one where we checked for, I think 8 different categories, and we give it the right behavior for each one. Okay. Well, typically we're not telling people about the weather. Okay. So what kind of things do we do with these structures? Well, a thing that we do often with a multi-way decision structure is some kind of a lookup. So I've created a decisions 20 lookup so that you can see how that code might work. Okay, so first what we're going to do, so this is the intention of the program is to be a simple lookup coded in line. Okay, which means that all the code is in the main. Okay, nothing has been refactored into a function. Okay. Okay, so here's what we do is that we prompt, please enter region code. This is some kind of a business application. So these would probably be sales regions or something like that. And we say 1, 2, 3, or 4. So those are apparently the legal values. Okay. And then we test it. So we say, if region code equal 1, then we give it, we say that the region name is equal to northeast. Else if it's equal to 2, southeast. Else if it's equal to 3, northwest. Else if it's equal to 4, southwest. Else, and here's where it's really important to have the else. It's invalid. Okay? So what value is it? Well, it's probably an integer because we never tested to make sure that we got an int. So if we got, if somebody typed in hi mom, it probably blew the code up. Okay, we haven't done something to check that yet. Okay, and we're not going to, so we're not quite ready for that. Although we'll see something in a couple of more examples right in this chapter that will help us to solve that. So, and then we're just going to print region code. Region code is region name, period. And we concatenated the region name and the period so they'd be right next to each other and no space between the region name and the period. Okay, so let's do some testing. Okay, so let's run it and make it a little bit bigger. So let's see, we'll give it a 1. And it says region code 1 is northeast. That looks good. And I'm not going to do them all. Let's just do a 4. So, sorry. Got to click down there before I put my 4 in. Region code 4 is southwest. Okay. So let's run it again. And so let's give it some invalid codes. Let's give it a 0. Region code 0 is invalid region. Okay, well that's pretty good behavior. Let's give it a 99. Okay, so this kind of a lookup from a list of values. We're trying to translate from, say, integer codes to some kind of a name that's a character string. Or you're just trying to categorize things. This kind of code is great for doing it. Okay? So the typical sort of extended multi-way is just what you need to do this kind of a lookup. Now, would we typically code something like this in line like this? No, I typically wouldn't, because I can describe what I'm doing in one line of code, right? And yet it's taking up about 10. Okay, and normally I want my code to be a little more succinct than that. Okay, so the next version I'm going to show you, we have simply refactored this into a function. Okay, so let's look at this. So this is one's, it's decisions 25, lookup refactored to a function, a simple lookup refactored to a function. And so the main code is pretty straightforward, and I guess I put the blank lines in here for drama. So again, I do the prompt to get the region code, and now I say region name equals lookup region name, and I pass it as an actual parameter, the region code. Okay, so it's returning a string, region name, and then I print it. Okay, so it does the same thing, but it does it in a much more succinct way, and it's maybe better documentation. What I like about this is that the function has a name that kind of documents what it does. And it also, you can look at it, well, what's the input? Region code. Okay. And what's the output? Region name. So it's pretty easy to understand what this code does because of the fact that we factored it into a callable function. One is it doesn't, it makes our code more kind of succinct and easy to read. And the other is it's a better documentation than the inline version. The inline version being back here, because we jump into this and yeah, we kind of recognize what we're doing, but this is usually a pretty small part of whatever you're trying to accomplish, and you don't want these lower level decisions to take over your code. Okay, which is why we like the lookup and function version. So I'm just going to run a test or two to show you it has the same behavior, but much better appearance, readability, maintainability. So okay, let's do 2. We haven't done that one yet. Region code southeast. And let's do 3. We didn't do that one yet. Region code northwest. And let's do another one that's out of bounds. Let's do negative 55, 55. And invalid region. Okay, that's good. Now with all these, we still haven't solved the problem of what happens if they don't pay attention and they give us characters instead of numerics. For instance, what happens if we put in the classic hi mom? Well, it's going to blow up. Okay, now we're eventually going to see the way around this, the way to guard against this, but we're going to show you a little bit in this chapter and a little bit in the next. So if you hang on, you'll see a little bit from here real soon. So simple lookups are pretty easy to do. Factoring them into a function is standard practice. One is it makes your code easier to read and easier to maintain. And it's, yeah, it come down to easier to read. It's better documentation. It's much easier when you can look at a piece of code and know what it does, because it's in a function that's properly named, and also what's the input and what's the output. Okay, and here, what it does, it's got a good function name, lookup, region name. What's the input? Region code. What's the output? Region name. It's perfect. Okay, if I do say so myself. Sorry about that. Okay, now what else could we do with these kinds of if-else functionality? Well, there are decisions that we have to make in a business application, let's say. And really, any kind of thing that we're doing, we need to classify things. Okay, so it's less of a lookup, it's more of a calculation. Okay, and the classic example that we give of this is calculating the premium for auto insurance on the basis of two factors, gender and age. Okay, and I've taught a lot of programming courses, and we've had a lot of versions of this. But I called this Decisions 30 nested in line. Well, what do we mean by nested? Well, as you can see, we have an outer decision is if gender equal male, okay, and then within the true and the false part, we have other decisions. So they are nested inside of the outer decisions. So this is said to be nested 2 levels deep. Okay, and when we read through it, it's pretty easy to understand. Could you go 3 levels deep? Yes, you could. The language will let you go very deep. I've never gotten to a point where it said it won't accept another level of nesting of if-elses. The problem is that while the language, the interpreter, is very good at keeping track of where you are, the human mind is not. And so in most programming shops, people say that 2 levels is okay, for sure. 1 level, great. Everybody does that. 2 levels, like this, okay. If you set it up the right way, if you format it the right way, if the variable names and the conditions are tested the right way, well, it's fine. In some places, they'll go 3 levels deep. Okay. Very few people think that going more than 3 levels of nested if is a good thing to do. So 4 levels, most programming groups would say, you've got to refactor the code so that they're not that deep. How could you refactor the code? Well, you can always take some code like this code right here, and you can extract it into a function. So if you wanted to have this be only 1 level deep, you could say if gender equal male, then you would call a function. Else, call another function. Okay, so these can be it's simplified by extracting methods or functions in this case, and but we don't want to get too complex. But this is this is pretty good. So what are the rules? Well, for a female, it's $100 if they're under 25. Otherwise, it's $70. I guess this is per month. Okay, for a male, it's $200 if they're under 25. Otherwise, it's $160. There are differences in auto insurance premiums for males and females, particularly when they're young, because young men can be pretty destructive in cars. Perhaps it's hormonal. In any case, it's statistical. Okay, so here's what we do. So we have a major test which breaks it up into male, and then the else assumes that the gender is female. Okay, a lot of times if you're doing this kind of thing, if you never actually explicitly test that the gender is female and you just assume it, it's nice to put a little end of line comment here to say that. And then within male, if the age is less than 25, then the premium equals 200, else the premium equals 160. That seems to correspond to the rules that we have. Okay, and then within the females, if the age is less than 25, the premium is 100, else the premium is 70. And maybe what I don't like here is I don't like the fact that we said 25.0. Let's just say 25. Let's assume that people are either 1 year or the other, and the years and the ages are integers. So I'm going to make that change, and when I upload it, you'll see that. Okay, so let's do some testing. Okay, so we're going to run this, and let's see what we get. Oh, what we did here is, this is one way to test it. You could just kind of experiment by hard coding the values in. So I hard coded in male and 24, and I got 200. So male, okay. If under 25, yeah, 200 if under 25, otherwise 160. Okay, that's good. Let's make the male 30. Okay. All right. Let's run it again. $160. Okay, that's good. And let's have a female and run that. See what we got. We can come down here to run it. $70. Yeah, that's good. And let's have a female that is less than 25. Let's make her 17. Okay. And give that a run. And she's going to pay $100. Okay. And again, why are premiums like this in the real world? Well, based upon statistical difference in the actual experience of drivers by age and gender. Okay. Okay, so this is a typical nested if. All right. Now, what if we wanted to extract this into a function? Okay. Again, it's a lot of code just to decide what the premium is going to be. Okay, because that's what we're doing. We're calculating the premium. What if we wanted to put that into a function? What would that look like? Well, my next example, 35 nested in function. So we're going to take the same code, okay, and don't pay attention to the main code for now. But we're going to take the same code and we're going to put it into a function called determine premium. Okay, well that looks good. And then we have two formal parameters, age and gender. Okay. And then let's not compare it to 25.0. Let's compare it to 25 because that looks better. We're going to assume that the ages are integers. Okay. And we've got the same code, except that here's what we did. We're getting in the age and we're getting in the gender, okay? And so we use these formal parameter names to make the decisions. And what do we do? Well, in every case, we populate the variable premium, okay? And then we return premium. So what are the inputs? Well, age and gender. What's the output? The premium, okay? So again, what I like about this is that it is, one is that it's easy to read. I think we're going to show in a minute it's easy to test. And I'm going to, you'll have to trust me, I think it makes it easier to maintain over time. Okay, now, what we're going to do here is we're going to show another kind of testing, and I want to begin by saying that this kind of testing that we're going to learn how to do is kind of a half step, okay? The same principles that we're going to be using here are used in these unit testing frameworks, okay? There are several unit testing frameworks even for Python. And they all have the same, all these modern unit testing frameworks have the same kind of underlying principles. And the principles are this. You want to define a number of test cases. Okay? So that's combinations of inputs. For each test case, you want to predict what the output will be. Okay? And then when you run the test case, you provide those test inputs and you compare the actual output to your expected value. And if they match, it passed. If they didn't, it failed. Okay, so here's what we're doing here. What we're going to do is we're going to pass in, we're going to call determine premium. We're going to pass in the first test case, it's going to be 18 and male. We're going to expect 200. 24 and male, expect 200. 25 and male, expect 160. 26 and male, expect 160. Okay? So what are we printing? Well, what we're printing here is a condition. We're saying if we call determine premium with 18 and male, we're expecting the answer to be equal to 200. If it comes back and it's equal to 200, we're going to print true. Now, typically when you run these unit test frameworks, you don't see true, true, true. You see pass, pass, pass. Some of them are even graphical. So when you run all of the unit test cases, everyone that passes gives you a little green bar segment. Everyone that fails gives you a red bar segment. And so you run all of the unit test cases and you're expecting to get all green. Okay? If you get a red, well, that means you either have a problem in your code, your production code, which in our case is determine premium, or in your test code. Okay? You don't know until you go check. It could be a bad test. It could be bad production code. Okay? There could be either place. Okay, so then what did we do for female? Well, we used the same age ranges because the cutoffs are the same. The cutoffs were at 25. So we have one that's less than 25, one that's just before 25, one that's at 25, one that's above 25. Okay? Now, how did we decide which ones to use? Well, this strategy for testing, it has a name. It's called boundary value testing. Once you have conditional logic, you need to be able to generate enough test cases to make sure that you've tested your conditional logic. Okay? So you're going to want to make sure that you've got test cases for male and test cases for female, because that's part of the decision logic. Do you need a third value? No, we're only anticipating males and females in this case. Perhaps when we have someday a wider concept of gender will work its way into auto insurance rates. But at this point, it's probably true. I don't know if they go by how people identify, if they do chromosome tests. I bet they try just to have people report, are they either male or female? It's probably identification. Okay, or perhaps it comes from their license. It's a real issue. If it hasn't already arrived, it's right down the road. But in our program, we're only allowing people to identify in these two kind of old-timey traditional categories of male and female. Okay, so we've got those covered, and then if the decision point is less than 25, well, we want to make sure that we test right around the boundary. So I want to make sure that I've tested 24, 25, and 26. So what do I have? 24, 25, and 26. And then I have one that's well below. I have 18, just to show what that's going to look like. Okay? And so let's give this a run. How does it run? Well, we run and we get true, 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 true. Okay? So this is one way to do unit testing, where we predicted the values. Okay? Good unit testing always says you predicted the combination of inputs. You've identified the significant combinations of inputs. You predicted the outputs associated with them. Every combination is called a test case. In this case, we've got 8 test cases with predicted outcomes, and we found a way to get Python to, in a pretty easy way, tell us if we passed all the test cases. Okay, so this is not quite automated testing, but it's an introduction to the principles of it. And however you're doing your testing, even if you're coding in each of the test cases by hand, say you're prompting the user for the age and the gender, well, then you have to keep track. You still need, some would say you need only 6 test cases. I went ahead and have one extra on each side, so I have 8. But you still need 6 to 8 test cases to make sure that you're testing this. whether you do it in some kind of a semi-automated way, which we see here, or whether you do it by inspection, which is that you key in the values at the console and then you compare the output to what you expect visually, that's inspecting the output, or whether you use a proper automated testing framework, the concept is the same. Okay? So there was our opportunity to see some unit testing ideas. The other thing that we saw here is we saw what happens when you print a condition. Okay, this is a condition. There's an expression on the left. There's a value on the right. We're giving it the equal test, and we're expecting to come back either true or false, ideally all true. Okay? And then the other thing that we talked about in this group of programs that we looked at is the fact that it's typical to have to nest these conditional, these selections or decisions. That's an example where they're nested two levels. Some people, almost everybody agrees that provided that you code them in this kind of understandable way, 2 levels is just fine. Some people say that it's okay to tolerate 3 levels, but almost nobody these days thinks that it's a good idea to go to 4 levels of nested if. And even though we haven't done it, how do we avoid having more levels? Well, you take the level that you want to get rid of and you extract it into a function. So we could do something like this. We could right click and we could say refactor extract method. Okay, and that's how we would do it. All right, so that's how you do that. Okay, let's go back. Let's go back to the slides. He talks a little bit about try except. So let's kind of see what that is. Okay. One of the things that you've noticed, I think, well, you've probably noticed a couple of relevant things. One is that it seems to be helpful to want to take some of our code and to package it into functions and to call it. Okay. Now, one implication of that is that things might go wrong in the called code. And the question is, how will the called code, especially if we're reusing that code for several purposes, how will it know how to behave if things go wrong? And it turns out that there's a construct in which it doesn't have to know how to behave. It just has to know how to signal that something's gone wrong. And that is exception handling. So exception handling in Python is particularly useful for when you're doing your work in functions or methods that you call, and you want to be able to detect if something went wrong in whatever code you called. Now, the first time that we do it, we're not going to have the problem happen in called code. We're going to have it happen right in line, and we can certainly detect that. He's talking about exception handling in terms of quadratic equations, and that's something that we don't want to talk about. But here he eventually gets into try except. So that there's a construct, okay? It's a decision-like construct called try, and then you have a body of code, and then you can code accept, and then you name the error type. And what happens is, if when executing the body of code, an error occurs, it pops out and it runs this exception handler. Okay, so what does he say? When Python encounters a try statement, it attempts to execute the statements inside the body. If there is no error, control passes to the next statement after the try except. So that would be down after the handler. If an error occurs while executing the body, Python looks for an accept clause with a matching error type. If one is found, the handler code is executed. So what is the handler code? Well, it's just like code block. It's a body. The original program generated this error, so that's his problem. All too mathematical for us. We're going to have a lot simpler errors when we get to my example. So I went backwards instead of forward. So the last line, so there are some interesting errors that we can check for. One that's going to be very interesting for us is called a value error. Okay? And we're going to see how that's going to help us get our code done. So let's actually get out to the code that I want us to work on. Again, quadratic equations don't really interest me in particular, and so I don't think that they're a good way to illustrate this kind of code. So we're going to go to decisions 40 try, and let's get a look. Okay. So here's what I have. So I say try, and I prompt for integer input. So I say, please enter an integer. Okay? Provided that that goes well, it's going to print, you have entered the integer some integer. Okay? If there's a value error, which is what happens if we don't give an integer, what happens if we give a float or we give an alphabetic, it's going to execute the code block hanging off of the except value error. So if it's a value error, it's going to say that was not an integer and you know it. Okay? We can also detect other things. One of the things that you can detect is a keyboard interrupt. Somebody stopped the program. Okay? Now we do that when we go to run it. If we click on the red stop button, it enters a keyboard interrupt. It stops the program. So what are we going to do? Well, we're going to skip a line. That's what the escaped new line character does, and it says, I detect a keyboard interrupt. Now that was just mean. Okay? And finally, what's this? Well, even if we found an error, we'll make sure to do whatever is in the finally block. So we print, let's put our toys away before we leave. Okay, and thanks for playing. All right, so let's do some testing, and then I'll explain it a little bit further. So I'll make it a little bit bigger. Let's run. Okay, so please enter an integer. 25. You have entered the integer 25. Let's put our toys away before we leave. Thanks for playing. Well, that went fine. There were no errors. Okay. All right. Let's run it again. See how when we run it over here, as long as the program's still running, you can click on the stop button. Okay? Let's click on that. Let's see what happens. Stop it. It says, I detected a keyboard interrupt. Now that was just mean. let's put our toys away before we leave. So it's going to do, let's put our toys away before we leave. Thanks for playing. Okay. Um, let's um, let's try to put in a float. Okay, so please enter an integer 25.0. That was not an integer, and you know it. Okay. Now, in the past, you'll remember that when we have tried to convert the input, the character input that comes at the command line. When we tried to convert it to an int with a call to the function int, if it's not an int, it blows up. What's happening is it blows up on a value error. Okay? This allows us to catch that error. We're catching an exception. In some languages, including Java, it's called a try-catch block. In Python, it's called a try except block because we use the keyword except. But we're catching a value error, and it's going to do our processing instead of blowing up. Okay, without that try except, if we did either typing in a non-integer or we clicked the stop button, we would have gotten the typical blow up stack trace thing. Okay, so what this allows us to do is to anticipate the kind of errors that can happen and to plan for them and to take appropriate action without the program stopping. Okay, now typically what we're going to do is if we want the user to type in an integer, we're going to catch it in just this way, but we're going to put it inside of some kind of a loop until either the user types in a proper integer or perhaps they stop the program. We could catch them both. So perhaps if they stop the program, they did a keyboard interrupt, we might say, oh, I'm sorry, you don't have an integer to put in, we're just going to stop. On the other hand, if they have accidentally typed a non-integer, we're going to prompt them again. The reason why we're not doing this yet is that we really haven't officially gotten to loops yet. Okay, we've been peeking ahead at loops. We did that in the early chapters, but the looping, the iteration, is not until next chapter. Okay? Okay, so what's this finally do? Okay, well, is there a difference between having that print, let's put our toys away before we leave, and thanks for playing? And it turns out that there is. Okay, there are times when we're catching exceptions. We're catching these exception conditions, and we want to make sure that some of the resources that we're using, like files that we've opened or database connections that we've opened, we want to make sure they're closed before we leave. Now, this is something we would do in some kind of complex web application framework code. Okay, so yeah, we can have a catastrophic error and we can catch it, but we want to make sure that we tidy up before we stop our portion of the program, or what's going to happen is that over time we're going to have a lot of memory that's been allocated to all these scarce resources. Memory is a resource, and they're not going to go away. So the finally is a way to make sure that we we take care of necessary business. Okay, and we might want to do that even if we were expecting to temporarily intercept the control to print out some messages, and then we wanted to leave. Okay, so these kind of happen at the same time, but finally allows you to make sure that you do things like close files and database connections and all that kind of stuff. Okay, it's not something we're going to be using a lot, but I wanted to show you that it was there. Okay, so this is a typical example of using a try except a block to detect a bad input in a code that's just in line. Okay, it's not in called code. Okay, now what if we were what if we had called code? Okay, so let's take a look at that. So let's look at 45 raise. Okay, now there's really, well, before we do this one, we're gonna try another one. Let's take 40 and let's create another version of it. So we're gonna copy 40. Okay, we're gonna paste it, and it's gonna be called 43, and it's gonna be try with called code. Okay, so what's this going to look like? Well, let's take this. Okay, and let's refactor it into a function or a method. So we went, we right-clicked and we said refactor extract method. It calls them all method, even though these are functions. Okay, and then the method name is going to be called something like, let's call it get my integer from user. Okay, and the output variable sum integer. Okay, so what's going to happen? Well, we factors out a function get my integer from user. Does it have any input? No. Does it have any output? Yes, it returns some integer. Okay, can things go wrong in here? Yes, they definitely can. All right, now what's going to happen? Well, the first thing that's going to happen is it's going to start to blow up. Okay, but then we're calling this code from inside of a try block. And instead of ending the program, it's going to say, oh, you know what? We can handle the problem that happened in get my integer from user. And then it's going to give us the same kind of services that we got when this code was in line. So let's try this. Sorry, it's now a little bigger. Just a little bigger. There we go. That all fits. All right. So this should run just the same as the previous version. So please enter an integer. Okay, 55. You have integer 55. Let's put our toys away before we leave. Thanks for playing. Okay, so that's the good case. All right. What if we run this and we give it the classic hi mom? It caught it. Even though the problem happened in called code, okay, our code was able to catch it. So what happens is that these these exceptions propagate up. So if main, if we've called get my integer from user from main, and there is an exception, if there's no code to handle the exceptions, if it isn't in a try except block down here in the called code, it just propagates up to where it's called from, and it says, well, is there a way to handle it here? And it goes, oh yeah, we're in a try block. Okay, well, great. So we handle it the same way that when the code was in line. Okay, what can we catch it if we hit the stop button? Let's just hit the stop button. Whoop, I detect a keyboard interrupt. Now that was just me, blah, blah, blah. So that worked just fine. So one of the nice things about these try excepts is that they not only work for inline code, okay, but they also work for code that you call. Both code that you call that you wrote, like the refactored version of how to get the integer from the user, or code that's part of a one of the Python packages. So when you're about to do something tricky with some Python package code, you can put the call into a try except block, and even though the things that go wrong may not go wrong in your code, that doesn't keep you from being able to recover from it. As we can see here, we were able to recover from this just as gracefully when the problem happened in called code as when the problem happened in inline code. Okay? And now we would be able to do something tricky. We would be able to write a general prompt the user for an integer and don't give up until you get one. We would be able to do that now, except that, as I said, we haven't really formally gotten to loops yet. Okay? So we'll try to do that once we get to loops. We have all the try except infrastructure that we need. Now we need a little more looping infrastructure, and we'll be able to build something like that that's pretty cool. All right, so that's try except. Okay, now what was raise? Okay, 45 raise. Well, what if you create, okay, what if you create some called code that can run into trouble? Okay. Can you actually trigger an error? Okay. You can. Okay. So for instance, you'll have a lot of situations, and here we're passing back region name, right? Okay. But there's a lot of times when we're getting in a number, we're passing back a number. There's no good way to send a message back in the region name that says this region name is invalid. Okay, so how do we signal from the called code to the calling code that something has gone wrong? Well, we can raise an exception. Well, how do you do that? Well, in this case, instead of putting some kind of a flag into region name, we just say raise value error. Okay? And a value error is one of the standard errors in Python. It means that you put in an improper value. We can reuse it for our own purposes. These error classes, when you create them, you pass them a string that has a description of the error. Region code must be 1, 2, 3, or 4. Okay, so let's run this. Okay. Run it. So again, we're asking for region code 1, 2, 3, or 4. So let's just put in 3. And region code 3 is northwest. Thanks for playing. That's good. Okay, so let's give it a wrong value. Let's give it 99. Okay. What we did here is that we intercepted this custom exception. So this is how you cause an exception to happen yourself, okay? And you can catch those too, okay? So we can say accept value error as VE. So this creates a copy of the value error. And then when you say print VE, it prints the string that we put in here. So we got region code must be 1, 2, 3, or 4. Okay? So what's really interesting is that these exceptions turn out to be a really ingenious way for code that's been called to signal to the calling code what's gone wrong without having to know how to fix it. Okay, and this is a really important part of well-designed code. If you're going to have reusable code, okay, the code can't know about every bit of code that's going to use it. So it can't always tell what the appropriate action is if something goes wrong, okay? But it can signal something went wrong and what went wrong. And then the calling code, it's up to the calling code to, if it wants to catch the exception and to recover from it if that's appropriate. And that's what we've done here. All right. If we didn't catch the exception, we would have had the typical code explosion down here with the stack trace and all that kind of stuff. Okay. So this turns out to be a really handy architecture for reporting errors up the chain of command. And again, it works. What happens when we're calling code from some Python package, if we anticipate that it might be having problems, we're able to catch it. Okay? And to recover from it if we believe that it's recoverable. Pretty cool. And then we can write lots of general code to be called that doesn't have to know how to solve problems. It only has to know how to report them. Cool stuff, huh? All right, that's all of that one. Okay, what's left? Well, we're getting down to close to the end of the chapter. Let's go back to where we were. So he does the exception handling. He's got a pretty nice discussion here of kind of general program design issues. Okay, and there's kind of a pattern that he introduces that I think is pretty neat. So let's give it a look. So once we have these decision structures, okay, well then we can write more useful logic. Okay, so for instance, what if we wanted to be able to decide on the max of 3 inputs? So now that we have decision structures, we can solve more complicated programming problems. The negative is that writing the programs becomes harder. Yeah, it does. Now, the takeaway when we're done with this is if you do a little good design thinking, it becomes harder, but not overly hard. Okay? So suppose we need an algorithm to find the largest of three numbers. So let's see. So we say def main x1, x2, x3 eval input. Please enter three values. Now he hasn't changed this. We're not using eval anymore. He had eval here in the last version. We're going to have to commit to whether we're getting integers or floats. So I would have been happier if he said max of three integers and used int here. But we're going to have to excuse them. That missed the changes for the third edition. Okay? So, and then he says, well, the missing code sets max to the value of the largest, and then print the largest value is max val. So I guess he meant max val, not max. Right? Okay. So this looks like a three-way decision where we need to execute one of the following. Max val equals x1, max val equals x2, max val equals x3. So one of these three assignments. All we need to do is to preface one of these with the right condition. Well, that's true. So let's look at the case where x1 is the largest. So we say if x1 is greater than equal to x2 and x3, max val equals x1. So he goes and he says, is this syntactically correct? And he said, many languages would not allow this compound condition. Python does allow it, though. It's equivalent to x1 is greater than equal to x2 is greater than equal to x3. And I just want to point out that even though Python will allow this kind of stuff, this isn't the kind of stuff that people do on the job in programming. Typically, when we compare things, we've got two sides. We have the left side and the right side. So this triple comparison works in Python, but again, I wouldn't want anybody on my team to do this. Whenever you write a decision, there are two crucial questions. When the condition is true, is executing the body of the decision the right action to take? So if x1 is at least as large as x2 and x3, so assigning max val to x1 is okay. Always pay attention to the borderline values. Now, we were talking about boundary value testing just a couple of minutes ago. So borderline values, boundary values, same deal. The ones that are close to the decisions, that's where you tend to make your mistakes. You tend to be off by one, okay? You use a less than instead of a less than equal. You use a greater than instead of a greater than equal. And then so your code does the right thing except for one particular value right there at the boundary. And in that case, it does the wrong thing. Secondly, ask the converse of the first question, namely, are we certain that this condition is true in all cases where x is the max? And he goes through these things. He's very math-oriented. So he can make two separate tests. So he's doing a three-way test, else if, a three-way test, else this. Now, to tell you the truth, this is kind of elegant programming, but I don't think it reads well. And again, these things with three components, they're probably not something that I would like to do. So he says if uh, he does this with an and. So if he says if x1 is greater than or equal to x2 and x1 is greater than or equal to x3, then it's x1. Else x2 is greater than x1 and x2 greater than x3, then it's x2x. Else it's x3. Okay, so I kind of get how that works. So we're comparing each possible value against all others to determine which one is the largest. Okay. It turns out there's an easier, more general way to do this, and we're not going to be too far from this. So this is an interesting strategy, but it only works for exactly 3 inputs. Okay? And sometimes, if we wanted to write general code, wouldn't we love to write code that would work for 2 or more inputs? Would it tell you what the largest one was? Well, this strategy is not going to work for instance, 4 inputs. So, again, this isn't a general way to do this. He talks about an approach called a decision tree. And he kind of talks you through this. So this is a decision tree. So if x1 is greater to equal to x2, then you chase out all the rest of the values. Else chase the other values. Okay. Again, this might be a little bit easier to understand than the first decision, but again, it only works for three values. Okay. It turns out that there is a way to do this through sequential processing. Now, there's a couple of things I like about this. One is it doesn't hurt your head quite so much. 2, you remember we had a whole chapter, chapter 5, on sequences. Okay, so processing sequences is a pretty general thing that we know how to do. We're going to do it with a loop. Okay, and while we're inside the loop, what if we were looking for the largest of something inside of a loop? Okay, so he says one strategy is to scan through the list looking for a big number. He's assuming they're numbers. When one is found, mark it and continue looking. If you find a larger value, mark it, erase the previous mark, and continue looking. This is pretty close to the way that you actually solve this problem. So he's going through the sequence, although looking at this in terms of a flowchart doesn't really, you don't really understand this. Oh, but you do, I'm sorry, I get what he's doing. So he says, here's what you do. You assume that the first one is the largest. You just assume it. You say, okay, the first entry is the largest entry. Then go to the next one. Is the second entry larger than the largest? Then it's the new largest. Then you go to the third one. Is the third entry larger than the largest? Then it's the new largest. So what we do is we create a loop, okay? We assume that the first one is the largest, and then we loop through the list. In this case, we'll use a list, at least in the program that I'm going to show you. We'll loop through the list, and then for each thing on the list, if it's larger than the largest one so far, well, then we'll replace the largest one so far. So when we get done, whatever is the largest one so far is the largest. It's just the way it works. It'll work for the largest. It'll work for the smallest. If you had a list of character strings, maybe you want to find the longest. Okay, work the same thing. You just would ask how long the string is. Okay, and if it's longer than the longest one so far, Well, then it's the longest one. So it's the new longest one so far. If it's shorter than the shortest one so far, then it's the new shortest one so far. So this kind of looping sequential strategy for finding the highest, the lowest, the longest, the shortest, it's a general pattern that you're going to be able to follow. Okay? Now, let's see that kind of code in action. Okay, so I have a decisions 50, find lowest. Okay, and let's just take a look at this. Okay, so we have what we need is we need some kind of a sequence. Okay, so what did we learn about sequences in chapter 5? Well, a string is a sequence of characters. Okay, well, it's possible that we could be going through a string of characters wanting to find the lowest character in the comparison order for Unicode. Okay, so maybe we could do that with a string. We could use a list. That's what we're using here. We could use a series of prompts to the user at the console. We didn't really think of it initially as a file, but it really is a file. The concept, the console is an input file. Okay, so we could do that. Or we could do a batch kind of program where we have a file, a text file of text lines, and we could read the input off of that. All those are sequences. This general pattern will solve all of them. When you're looking for, again, the highest, the lowest, the longest, the shortest. Okay, so this is the general look. Okay, so we have here, we say these look like they're going to be integers that we're using. And we have a list is 1, 5, 99, a minus, a 0, 23, 55, 96, a negative 2048, a 4096, and a negative 99. Okay, so what are we looking for? Well, in this case, we're looking for the lowest entry so far. So there's a couple of tricks in this program that I want you to think of. Trick 1. Do we want to go comparing things if this is an empty list? I'm going to warn you that you don't. Okay? If this is an empty list, there is no lowest. It's just empty. Okay? So I've got at the top level, I have a two conditioned, a two-way test. So I say if the length of the input list equals 0, print the input list is empty. We're done. Okay? We're not going to go try to compare things because it's going to blow up when we do it. Okay? Otherwise, then the first thing we're going to do is we're going to assume that the lowest entry is the first one. That's index 0. Okay? So we say lowest entry so far equals input list 0. Now we're going to iterate over the entire list. Okay? And then for entry in input list, if the entry is lower than the lowest entry so far, then the lowest entry so far now becomes the entry that we have. It's the new lowest. So we just go all the way around. Then we get to the end. We say there are length of input list entries in the input list. I just wanted to have some kind of parallelism between having said the list is empty. I want to say how many entries there are. And then I say the lowest value is, and now here's what I do. I take the lowest entry so far, which is an int. I turn it into a string, and I concatenate a period on the end so that the period is right after the number. if I had string is lowest entry so far, comma, period, I would have had a space in front of the period, and I wanted to avoid that. So how do you combine a number and a closing period in a sentence? Well, convert the number to a string and concatenate the string result with a period. Okay, so let's predict the outcome. Okay, so lowest, -1, that looks slow. Well, let's kind of play a computer. The lowest one is, let's say it's 1. Okay, that's the way this works. Okay, so then when we start again, we look at the 1. We know that's the same. The 5, no, that's not lower. The 99, no, that's not lower. The -1, that is. So -1 becomes the new lowest entry so far. 0, not lower. 23, not lower. 55, not lower. 96, not lower. -2048, that's a lot lower. Okay, so -2048 becomes our new lowest so far. Then we go 496, not lower. -99, not lower. So when we're done, we should have -2048. And then how many entries are there? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I'm expecting 11 entries, and the lowest is -2048. All right, so let's give it a run. And what did we get? There are 11 entries on the input list. The lowest value is -2048. Okay, now a test of this kind of approach is that what happens if we got an empty input list? Okay, how could we get that? Well, let's say that next chapter, we're going to be learning about how to do a loop where the user tells us, the loop's over. I'm done giving you numbers. Okay, what if they signal that the first time in? Well, then it's an empty sequence. Okay, what if we have a text file and we go to open the text file and there are no lines in it? Well, we have an empty sequence. Now, how do we simulate that with lists? Well, you just have a list with no members. So in addition to passing the test we already gave it, I'm going to also ask it to pass with this. So let's take the original list and toggle it into a comment, the empty list, and turn that on. And let's see what happens if I give it an empty list. It should say it's an empty list and then stop. Let's see. Run. Says it's an empty list and it stopped. Okay. If I didn't have this check up front, it would have exploded when I asked for the first entry and it knew it was empty. That would have thrown an exception. And of course, we don't have this code in a try except block, and so the program just would have stopped. Okay? So that's it. Okay, let's see if he has any other code that he wants to show us that I want to talk about. I don't think so, but we'll see. He's got code here that finds the max of a series of numbers. Okay, the same thing. You just want to keep track of the largest one so far. So it'll work with any extreme. The highest, the lowest, the shortest, the longest. You just have to keep track of the whateverest so far. and you just assume that the first one is that one, and then you compare each one to that, and you replace the whateverist so far if the next one you find is whatever, higher, lower, longer, shorter than the preceding one. Okay? So, some lessons. There's usually more than one way to solve a problem. Don't rush the code the first idea that pops out of your head. Think about the design and ask if there's a better way to approach the problem. Your first task is to find a correct algorithm. After that, strive for simplicity, efficiency, scalability, and elegance. So, in particular, I generally like a code that you could either automatically or easily turn into a solution to a more general set of problems. So the reason why the algorithm that we just went through to find, the biggest or the smallest or the whatever of a sequence, one of the reasons that one is good is it will work for a sequence of any length. And if you saw what we did, it'll even work for the empty sequence. One of the best ways to formulate an algorithm is to ask yourself how you would solve the problem. The straightforward approach is often simple, clear, and efficient enough. Now, I'm going to stop here. I'm going to take a little bit of exception here. You would solve the problem of the highest or the lowest. You would solve them the same way we solved it if you had a long list. Okay, if you had a long list, just the same way the program solved it would be the way to do it. Because you wouldn't be able to look at the list all at the same time. So you'd need some kind of methodical way to do it. Okay? If you went from page to page on the list and you saw a number and you go, oh, is that higher than the numbers were on page 2? I don't remember. So you would have to keep track of the highest one so far. Okay. On the other hand, if you had a short list, how would humans do it? They just look at the list. Okay. So humans, in the right context, can be very, very fast. And solve it in a very intuitive and visual way. It's only when we get a lot of data that we have to resort to solving the problem the way the computer does. Okay? So for me, it's not only how would I solve it, it's how would I solve it if I had a whole lot of these and I had to do it in a kind of a boring, rote, repetitive way, because that's what computers are really good at. Generality is good. I mentioned this before. So consideration of a more general problem can lead to a better solution for some special case. If the max of n a program, it's just as easy to write as the max of 3. Write the more general program because it's more likely to be useful in other situations. So, of course, you can get carried away with this, and you can write code that you're never going to use for more than the problem that's at hand. But generally, a general solution is going to be better than one that only works for, say, the number of things or the type of things you have at hand. Don't reinvent the wheel. So if the problem you're trying to solve is one that lots of other people have encountered, find out if there's already a solution for it. Okay, and this could take a couple of forms. One could be maybe there's a built-in solution, right? So, for instance, if we're trying to find out how many items we have in a list, we can iterate over them and count them, or we can call the length function. Okay? Well, given that there is a length function, writing the code to iterate over the list and count it is not time well spent, right? The other thing is there may be a pattern that either you know about or you don't yet that people follow to solve this kind of a problem. And the pattern that we just saw is the one that works for the biggest, the smallest, the shortest, and the longest. Okay? So that was a pattern that we resorted to. As you learn to program, designing programs from scratch is a great experience, but truly expert programmers know when to borrow. Okay, so there are times, and I tried to point them out, there are times when we'll have you build something that there's already a built-in function that will do, just so you can appreciate building things with that kind of architecture. But generally speaking, if there's a pre-built part that will do it, you want to use the pre-built part. Why? Well, every line of code you write, you not only have to design it, but then you have to write it. And then you not only have to test it, but you have to maintain it over time. So to the extent that you can use pre-built parts instead of designing and using custom parts, you can save a tremendous amount of effort over the lifetime of the program. So that's it. That's the last of the slides. In this particular chapter, the exercises that I'm going to give you are going to be kind of inspired by the examples that I went through in that supplementary project, the one that I have for you to download, Demonstrations to Supplement Zelle 3E Chapter 7. So I'm not going to do separate tutorials, but I am going to point out the sample program or programs that are most like the problem that I'm trying to have you solve. Okay, so you can use those as a reference when you go to do your exercises. So good luck on that, and I'll see you next time. Bye-bye.